Alright, welcome. Let's do some integrals. Let's do some practice. Okay, I'm going to be working a bunch of definite integral examples in this video, and I'm going to be working through BC Homework 6.2, which is a pretty robust homework. Okay, it's got 20 regular definite integrals, just like some drill problems, and then it's got a couple more pages of more situational problems. So it's going to be some good practice for us. All right, so let's just get to it. Number one, integral from 0 to 8 of 1 over the square root of x plus 1. I'm going to rewrite that as x plus 1 to the negative 1/2 power. Right, I had 1 over the square root of x plus 1, but in order to anti-differentiate this, I'm going to need to just write it as a power. Okay, an antiderivative for this is going to be, well, at least my hypothesis is going to be leave the inside the same, add 1 to the power, and then divide by the new power. Then I'm going to just mentally check and see what would happen if I took the derivative. Would I get the integrand? Okay, half of 2 is 1. Reduce the power by 1. Okay, that's good. And then the derivative of the inside is 1, so I feel good about this. Okay, that's an antiderivative. I'm going to plug in 8, plug in 0, and subtract. So that's going to be 2 times the square root of 9, right, because that's the 1/2 power, 8 plus 1, minus 2 times the square root of 0 plus 1. And that would be 6 minus 4 is 2, or you could just leave it like that, whatever you feel. Number 2. Integral from 1 to 2 of x minus 4 over x squared. So I might call that x to the negative 2 times x minus 4. Use the algebra before anti-differentiating. Okay, so this is going to be x to the negative 1 minus 4x to the negative 2 dx. Okay. Anti-differentiate this. You try to use the power rule. You try to divide by 0, and x to the 0 divided by 0 is not an antiderivative for any type of function. So this is going to be natural log absolute value x, okay, minus 4x to the add 1 to the power, and then divide by the new power. Okay, so that'll become plus. Okay. That's an antiderivative. I'll evaluate that between 1 and 2. And that will be log of 2 plus 4 times 2 to the negative 1. So that would be log of 2 plus 4 over 2 minus, when I plug in 1, log of 1 equals 0 plus 4 divided by 1. So that's just 4. Right, so I could say that's 2 minus 4 is negative 2 plus log 2. So just like that. All right, number 3. Integral from 1 to 2 of x to the negative 3 dx. Okay, I'm going to add 1 to the power, divide by the new power, and evaluate that between 1 and 2. Okay, what I might do, one thing you can do here is if you've only got one term, or if you've got that negative 1/2 on all the terms of your antiderivative, you can factor out the negative 1/2, and I'll say that's negative 1/2 of, okay, x to the negative 2 is 1 over x squared, so 1 over 2 squared is 4, minus 1 over 1 squared is going to be 1. We could take this farther if we had to, but we don't, so I'm going to stop there. All right. Oh, this one's nice. Still integrating 1 to 2. A lot of 1 to 2 here. Okay, x squared minus 1 is, I need to factor and cancel, right? Because we don't have a quotient rule for this stuff. Divide by x plus 1. So this is going to be, I'm going to anti-differentiate x minus 1. So what's going to happen? So it's going to be antiderivative for x is 1/2 x squared. Antiderivative for negative 1 is negative x. We're going to let that run 1 to 2. And that's going to be the value. I don't know. I'm not gonna worry too much about what that actually is. You could calculate that if you wanted to. I suppose I could too, but I could also make an error. That would be bad. So we're happy. That was number 4. Number 5. Integral from 0 to pi over 3 of sine of 3 theta d theta. Okay. The antiderivative step, we have to be a little careful because of that 3 theta, right? So I'm going to say, okay, an antiderivative for positive sine would be negative cosine. But then I need to be careful about that 3. I think I'm going to need to divide by that 3 to prepare for the chain rule, because I would have positive sine of 3 theta times 3 for the chain rule. So I need to divide by 3. So instead of negative cosine, I'm going to have negative 1/3 cosine of 3 theta. And we'll let that run from 0 to pi over 3. Okay. Again, I'm going to, because there's that here, I'm going to factor that out, because there's only one term in my antiderivative, so I can factor out whatever I want. And this will be negative 1/3 of cosine of pi. And maybe, okay, that's kind of out of the shot, but here is still in. Okay, there, okay, that's where pi is. The x-coordinate, that's cosine, it's negative 1. Okay. Cosine of 0 is going to be positive 1, because that's going to be over here. Cosine of 0, why did I do that? All right, can't find my eraser. Okay. There we go. Okay, so that's negative 2 times negative 1/3 is 2/3. Okay, that's how we did that one. You're all right. All right, so this one, I mean, if you wanted to, you could maybe try to reverse engineer, you know, increase power by 1, divide by the new power, also divide by the slope of the inside, because the inside's linear. Could do that if you wanted. I think what I'm going to do instead is I'm going to just actually square this thing. So if I square 3x minus 2, I'm going to get 9x squared. Okay, I'll have negative 6x, and another 6x is minus 12x plus 4. I think that's what y'all should do at this point. So what's going to happen is I'm going to say that's equal to an antiderivative for 9x squared is going to be 9x to the third divided by 3. So 3x to the third minus 6x to the 2 plus 4x as x runs from 0 to 1. So that's going to be, when I plug in 1, I'm going to get 3 minus 6 plus 4. When I plug in 0, I'm going to get 0 minus 0 plus 0. And that'll be, you know, 1. Oh, that's kind of surprising. Whatever. Let's keep scrolling that up a little more. 7. Okay, this one I'm also going to have to hit with algebra. It's going to take 2 steps of algebra, which is a little unpleasant. And I guess, you know, in the next lesson you will learn about a method for dealing with this where the derivative of the inside of a composite function appears on the outside with multiplication. But we don't have that yet. We don't have U substitution. So what we're going to do is we're just going to actually square x squared plus 2 and then distribute in an x. And maybe I'll do that work off to the side, though. So x to the 2 plus 2 squared. Whoops. Okay. And so if I was to multiply an x onto that, I'd have it like that, and that would be x to the 5 plus 4x to the 3 plus 4x. So now I'm integrating from 0 to 1, x to the 5 plus 4x to the 3 plus 4x dx. Okay, an antiderivative for this is 1/6 x to the 6th plus 4x to the 4 divided by 4, so just 1x to the 4, plus 4x to the 2 divided by 2, that would be 2x squared, as x runs from 0 to 1. Okay, so that's going to be equal to 1/6 plus 1 plus 2 minus 0 plus 0 plus 0. Right. Ooh, there we go. This next one is, nope, that I was looking at the wrong problem. I was looking at 11. I'm looking for 8. So for number 8, this is the integral from 1 to 2 of 4x to the 3rd minus 6x. Okay, so I anti-differentiate. That's going to be x to the 4th minus 3x to the 2 as x runs 1 to 2. Okay, 2 to the 4 is 16, minus 3 times 4 is 12. And then when x is 1, I've got 1 minus 3. And that's cool. I think that's going to be 6, but you know, not worth a hair. 9. Okay, the integral from 0 to 1 of the square root of x times x plus 1. Okay. And I'm going to again do a little bit of algebra off to the side. Right, because that's x to the 1. When I distribute and multiply them, I'm going to add the exponents. And this is 0 to 1 of x to the 3 halves plus x to the 1 half dx. So I get an antiderivative. I add 1 to the power. So that's x to the 5 halves. Divide by the new power. That's like multiplying by 2/5. X to the 1 half. I've done that antiderivative enough to know that's 2/3 x to the 3 halves. And I'm going to go from 0 to 1. Okay. And then this is going to be equal to 2/5 plus 2 minus, plug in 0, and I get 0 plus 0. Okay, I've noticed that, I don't know, this only happens to be if you're watching this particular example, but I've seen a lot with the lower bound of 0 where then when you plug in and you get 0 and you're subtracting away, you need to plug in and make sure that that's 0 every time, because there are things like exponential and cosine and secant and other and composite functions that you plug in 0 and you might not get 0. So you can't just say, oh, it's 0 to 1, I'm just going to plug in 1 and that's going to be the answer. You cannot do that. It's not a good idea in this class. Okay, so number 10. All right, integral from 1 to 2 of 1 over x squared dx. What you want to do on this one is write that as x to the negative 2. Okay, so you don't fall into the trap of saying this antiderivative has anything to do with natural log. It doesn't. Okay, if you were to try to figure out an antiderivative of this thing, like say log of the absolute value of x squared, take the derivative of that and convince yourself that that's not an antiderivative for 1 over x squared. Okay, it has to do with the chain rule. So I'm going to, I'm going to execute the power rule here. I'm going to add 1 to the power, divide by the new power, and let x run from 1 to 2. Okay. I might actually say that negative x to the negative 1, that's negative 1 over x, as x runs from 1 to 2. And that will be negative 1 over 2 minus negative 1 over 1, so that's equal to positive 1 over 2. Okay, that's number 10. Number 11, 0 to x of sine t dt. Okay. Well, I find an antiderivative for sine t, and that's negative cosine t. as t runs from 0 to x. Okay. And that's going to be negative cosine of x minus negative cosine of 0, so that's plus cosine of 0 is 1. So negative cosine x plus 1. What you'll find is that this is one of many antiderivatives for sine of t, including negative cosine, well, specifically negative cosine of x plus 1. Oh, yeah, sure. This is an antiderivative for sine of x. We'll talk more about that later, with the dummy variable and all that stuff. Okay. I'm going to do one more of these, then I'm going to take a break and eat my lunch. So, for 12. Integral from 1 to e to the 3 of x squared minus 1 divided by x. Okay, so I'm going to say that this algebraically is like 1 over x multiplied by x squared minus 1. That's going to be x to the first minus 1 over x. And that's going to be, okay, an antiderivative for x is 1/2 x squared minus log absolute value of x. As x runs from 1 to e cubed. All right, whatever. This is going to be, when I plug in e to the 3, I'm going to get e to the 6 divided by 2 minus the log of the absolute value of e to the 3. The absolute value of e to the 3 is e to the 3 because that's a positive number. The log of e to the 3 is going to be 3. It's a special exponent I put on e to get e to the 3. That would be 3. And when I plug in 1, I get 1/2 minus the log of 1, which is 0, because it's the special exponent I put on e to get 1, which is the 0 exponent. Okay, and then that's going to be plenty for our purposes here. Okay, number 13, integral from 9 to 25 of y to the 3 halves dy. We're going to antidifferentiate y to the 3 halves. We're going to add 1 to the power, divide by the new power. And we're going to let that run from 9 to 25. And, you could definitely say that was 2/5 of 25 to the 5 minus 9 to the 5 halves. And I might end up needing to stop there because I'm thinking, I don't know what 5 to the 5 is. Yeah, I don't have that. I have 5 to the 2, 5 to the 3 is 125, 5 to the 4 is 625. I don't know what 625 times 5 is, so I'm just going to stop there, and that's going to be a suitable answer. I also am not sure about 3 to the 5th. I think that's 243, but better safe than sorry, right? So, 14, integral from -1 to 2 of 6x minus 3 dx. Okay. Antiderivative. Plug in top, plug in bottom. Maybe I'll go down here. So 3 times 4 is 12, minus 3 times 2 is 6, minus 3 times -1 squared would be 3 times 1, and that's just going to be 3, plus 3. Okay, and that's 6 minus 6 equals 0. I think, hold on a second. Oh, I see it now. I was thinking that thing had a 0 at x equals 2, and that's just not true. At x equals 2, the value of 6x minus 3 is 9. But what I will draw you is that this thing, it's a line, it's a pretty steep line. And what we just did was we just computed that the area from -1 to 2, the net signed area was 0. Okay, so this amount of area was equal to that amount of area. What actually happened there is that halfway between -1 and 2 is x equals 1/2. which happens to be where the x-intercept of this line is. So that's why it ended up being 0, right? It's because this amount of area here was equal to that amount of area there. Okay. I fit one more in on this page. Yeah, integral from 3 to 5 of 7 dt. Right? So on one hand, I can say, okay, this is 7 as x runs from 3 to 5. So it's a rectangle with a width of 2 and a height of 7, so that area is 14. And so I know this integral needs to come back 14. But maybe you want to do this using the fundamental theorem of calculus, which you just learned. So I'm going to get a different color and go over here and find an antiderivative for 7 with respect to t, and that's 7t, as t runs from 3 to 5. And that equals, okay, I might even factor out that 7 and say that's 5 minus 3. And so you can see why it does end up working like that rectangle, height of 7, width of 5 minus 3. Okay. So, how do you want it? It's going to be 14 either way. Number 16 now. This one, I know this, I've got a multiple choice question. It's a lot like this. And you know where I use the multiple choice, so it might be good to remember this one. Number 16, integral from -6 to 3 of x over absolute value of x dx. Okay. This one, we don't have an antiderivative for this, or actually, maybe we do. I don't know. Maybe you know an antiderivative for this function, and if that's the case, then you just do that. But I'm not, in general, suggesting that's what the students in my calculus class should do. So I'm going to actually just draw a picture. That's the x-axis. Here's the y-axis. Absolute value of x divided by x looks like. So maybe that's -6 and that's 3. Okay, so that will have area -6 because this goes down to -1. This will have area +3. And so this is equal to -6 plus 3. Okay, which is going to equal, hold on, -3. All right, number 17. Now this one's going to require a little extra anti-differentiation magic. So I'm going to integrate from 1 to 5, 3 to the t dt. So what I need to do is I need to find myself an antiderivative for 3 to the t. So what I'm going to do is I'm going to say, well, 3 equals e to the natural log of 3, meaning 3 to the t equals e to the log 3 to the t, which is the same as e to the log 3 multiplied by t. And so if I was going to anti-differentiate that with respect to t, it would be the same as anti-differentiating that with respect to t. Okay, so an antiderivative of e to the log 3 times t. If I had e to the 2t, the antiderivative would be e to the 2t divided by 2 to prepare for the chain rule. So this one is going to be e to the log 3t divided by log 3. So log 3 is just a number, kind of like the 5 and the e to the 5t, or e to the 2t, 2 and e to the 2t. We're going to divide by it to prepare for the chain rule, and then it plus any constant. But I know that when I'm running a definite integral, I don't need to worry about the plus c because it would subtract away from itself whatever the value of c was. We just assume c is 0. All right, and then, hold on, I've got another step. I go and I say this, wait a second, that's 3, the thing I just boxed. So this is 1 over the log of 3 times 3 to the t, okay, plus c. Plus any c, and this can be any antiderivative for 3 to the t, so I'm just going to choose c equals 0. Okay, so 1 over log 3 times 3 to the t as t runs from 1 to 5. Again, this 3 to the 5 thing, and it's 3 to the 4 is 81, so yeah, 243. All right, so I've got 1 over log 3 multiplied by 3 to the 5 minus 1 over log 3 times 3 to the 1. Okay. And that's going to be the value of that integral. Okay. This, while I'm here, this is not one that you just absolutely have to know for my class right now, but in the long term, that is one that we're going to have to know for AP Calculus. 18. Right, integral from pi over 3 to pi over 3 of anything is going to be 0, but yeah, sine of x squared dx, that equals 0 because it doesn't have any area. Okay. Or suppose I could find an antiderivative for sine of x squared with respect to x, which you can't. Some functions are not antidifferentiable. If I could, and I plugged in pi over 3, and I plugged in pi over 3, and I subtracted them from each other, no matter what the antiderivative was, I'd get 0. So that's another reason why integral from a number to that same number is 0, in terms of the fundamental theorem instead of in terms of area. All right, 1 to 16 of the 4th root of x, I'm going to write that as x to the 1/4 power. And then I'm going to anti-differentiate. Whoops, thought I was recording. I was still paused. So I anti-differentiated, which I added 1 to the power divided by the new power, let it run from 1 to 16. Plugged in 16 to the 5/4. What you need to do is take the 4th root of 16, and that's 2. Then take 2 to the 5th power, and that's where I got 32. Minus 4/5 of any power of 1 is 1, so 1 to the 5/4, that's 1. Okay, 4/5 of 32, I could factor out the 4/5 and call that 4/5 of 31, and say that was, well, 124 maybe, divided by 5. It's not worth it, right? Just stop here. Okay, that's plenty far. Okay, the last one, number 20. And this one's a little tricky, right? Because we're not going to have an antiderivative for this. We need to draw a picture and use geometry like last time. So, and evidently I made an error when I was doing this one on the video last time. So, negative 2 to 0 of this. All right, so I'm going to draw a picture. And pardon me, I'm just recording some solutions to a homework, and like it's almost, well, I'm almost done with this part of the problem. So, like, I'll just finish this one and I'll be quiet. This is a half circle centered at the origin, radius 2. If I'm integrating from negative 2 to 0, that's this part of the circle. It's a quarter of a circle, so it's a quarter of pi times radius squared. All right, now the next problem is got a piecewise defined function, and we're going to try to integrate it. And I think one thing I want to tell you about a piecewise function is that, you know, if the pieces are continuous, then we will be able to integrate. You know, like the conditions for Riemann integration are that the function that we are integrating over is at least piecewise continuous. Okay, so we need to be integrating on continuous regions, but we don't really run into anything that's like horribly discontinuous. Like it's like got an interval of discontinuity or discontinuous everywhere. Nothing like that. We don't run into those functions. We're mostly interested in continuous functions in this class. So I might draw a picture of this thing. This is 3 until x equals 2. And then it's 5 minus x after that. And so it will look like that. Okay? So we could do this using geometry, or we could, you know, we could integrate 3 from 0 to 2 and 5 minus x from 2 to 5. But I'm telling you, integrating 2 minus x from 2 to 5 and plugging in, you know, anti-differentiating, plugging in top and bottom, subtracting is probably not the thing to do. Especially when we can kind of just see what's going to happen here. So this has a width of 2 and a height of 3. This is a triangle that's 3 and 3 this way. So it's going to be 3 times 2 plus 1/2 of 3 times 3. All right. Table of values for f and its derivative f prime is given below. Okay, integral from 0 to 4 of f prime of x dx. Find an antiderivative for f prime, that's f. Plug in top and bottom and subtract. So that's going to be f of 4 minus f of 0. It's a fundamental theorem of calculus. So f minus f of 0 is 6 minus 2 is equal to 4. Okay. This is going to be equal to the integral from 2 to 4 of 5 dx. Minus 3 times the integral from 2 to 4 of f prime. Okay. The integral from 2 to 4 of 5, that's going to be a rectangle with width 2 and height 5, so it's going to be 10. Minus 3 times, okay, well this is just going to be the net change in f from 2 to 4. So 6 minus negative 3. Okay, so 10 minus 27 is going to be negative 17. right, so the integral from 1 to 0 of this, and I might just find an antiderivative for this, plug in 0, plug in 1, and subtract, because I'll just show you, we can't do that. We don't have to always reverse the bounds anytime it's, where the greater bound is on bottom. We don't have to. Just sometimes it's the better thing to do. Anyway, I'm going to anti-differentiate 4x, and I'm going to get 2x squared. I'm going to anti-differentiate f double prime of x. I'm going to get f prime of x. We're going to let that go from 1 to 0, so I'm going to plug in 0 first, so that's 2 times 0 squared, plus f prime of 0. And then when I plug in 1, I'll get 2 times 1 squared is 2, plus f prime of 2 is 5. Okay, so I got 1 minus 7 is negative 6. All right. Find the values of b for which the integral from 1 to b of 8x plus 4 dx equals negative 16. This is a good question. This is related to a multiple choice question that I know, just for what that's worth. So I'm going to anti-differentiate. That's going to be 4x squared plus 4x as x runs from 1 up to b. So that's going to be, I'm going to plug in b, 4b squared plus 4b minus, when I plug in 1, I'm going to get 4 plus 4. Okay. And I want to know where this is, this integral, I just computed, is that in terms of b, and that's equal to negative 16. So I'm just going to find out the values of b that make this equation true. So I'm going to add 16 to both sides, and I'm going to get 4b squared plus 4b plus 8 equals 0. So I'm going to factor out the 4, and I'll get b squared plus b plus 2. That's not good. Hold on. Okay, yeah, I think I had meant to change this question so that the area equaled 0, but, I didn't. So, okay, 1 squared minus 4 times 1 times 2 is a negative number, so this quadratic b squared plus b plus 2 is not going to have any real zeros. Okay, so I'm going to say no values of b. What we'll do is I'll show you what would happen if, say I had changed this to, instead of negative 16, I'd changed it to be 0. This stuff would be the same, and this negative 16 would become 0. So I'd have 4b squared plus 4b minus 8 equaling 0. I think this is what I'd meant to have happen. Okay, I can factor and then get actual values of b, okay, and it would make sense that b equals 1 would be one of them that would give you a 0 area, but I just figured I'd throw that out there. And also, I think f prime of 1 is equal to 2, and I miscopied that, so that's going to be 1 minus 4 and not 1 minus 7. Okay, so suppose integral from 1 to 5 of g of x dx equals 6. Find the value of the integral of g of x plus 7 on the same interval. Okay, what I'm going to do is I'm going to split this out over its addition, which is a property we have. 1, 5 g of x plus the integral from 1 to 5 of 7 dx. And okay, I've already got this, that's equal to 6. That's what they told me in the statement of the question. Plus this one, I'll take this out to the side. I'll say from 1 to 5. And we'll say that's 7. So it's a rectangle. It has height 7 and width 6. So that's area 42. So that's 6 plus 42, and that's going to be 48. Okay. Now let's talk about some average value. Okay, so we're going to do average value by adding everything up and then dividing. Okay, so average velocity over 0 to 12 is going to be 1 over 12 minus 0 times the integral from 0 to 12 of v of t dt. That's how we find an average value of v. So we run an integral of it, we divide by the width of the interval we're integrating on. All right, so we're going to use a midpoint Riemann sum to do this integral. So this is about equal to 1/12 of, and now if I'm going to do 3 subintervals of equal width, so these are my subintervals from 0 to 12, and okay, this is v versus time. Okay, yeah, and so we're going to use the midpoint of each interval. Here's one, there's the other one, here's the third. Okay, I'm just going to assume that's 65. I don't know what else to say. I'm just going to have to assume it's 65. Let's see what I did last year. That's not the homework key I was looking for. Let's see. Okay, I said 68 last time I did this homework, so I don't know, maybe I'll say 67 this time. It doesn't matter. Like, if you can't see, actually, if it's not a grid intersection point, you just do the best you can. Okay, so height is 20. Width of the subinterval is from 0 to 4, so that's 4. Plus height is 50. Width of the subinterval from 4 to 8 is also 4. Height is 67 times width is 4. And then that's something that we could, run through a calculator if we needed or whatever. All right, the graph of y equals f of x is shown below. Average value of f. So f's average is going to be equal to 1 over 6 minus 1 times the integral from 1 to 6 of f of x dx. Okay, so what we need to do is just find out what is that area between 1 and 6. So 1, 2, 3, 4, 5, 6, 7, 8 and a half. Okay, it's occasionally some square counting in this class, and that's what we're going to do. And that's going to be pretty much, that's it, right? Because I've found, that area represents the integral. Divide by 5 to find the average value, and that's it. So, and if we needed to figure out what this was, maybe I'll also throw that out there. So maybe I'll say, okay, dividing by 5 is not super easy. I don't know, maybe you just know what 85 divided by 5 is, but I'm not super sure. 17. But what you want to do instead is divide by 10, right? So double the top and the bottom. So that becomes 17 divided by 10. Yeah, definitely. And that's 1.7. And that seems kind of believable, that for most of the time it's up here at either 1 or 2. And it's kind of spending a little more time above 1 than at 1. So it would make sense that average value would be above 1. Anyway. Suppose C of t represents the cost in dollars per day of heating your house. T is measured in days since the cold front hit last week. Interpret the integral from 0 to 1 of C of t dt in the context of the problem. Oh, okay. Rate of cost in dollars per day. Okay, so if we add up a bunch of dollars per day over the course of time, as we go from 0 to 21 days, that's going to give us the total cost on the 21 days. So okay. Interpret the integral from 0 to 21 of C of t dt divided by 21 in the context of the problem. That's going to be the average value of the cost. So that's average cost of heating the house between 0 and 21 days. And I might mention that this is measured in dollars per day, right? Because it's an average value of C, and C is measured in dollars per day. So, you know, and it's like you add up to get a bunch of dollars here, but then you're going to divide by a number of days also to get that average value. All right, just a couple more. If the average value of f is 4 on the interval 1 to 6, 5 from 6 to 8. Oh, this is a good question. All right, so here's 1, there's 6, and this is going to be 8. All right, so first of all, they said average value is 4 on 1 to 6. So the integral from 1 to 6 of f divided by 6 minus 1, well, that's equal to 4. So the integral is going to equal 4 times this 5, which is going to be 20. And then over here, on 6 to 8, the average is 5. So 5 is 1 over 8 minus 6 times the integral from 6 to 8. Okay, so if I was trying to solve for this integral to find out how much area to put in that box there, I'm going to multiply both sides by this 2 to get rid of the fraction. So that means that this area is 10. And if I want to know the average value of f on the interval 1 to 8, I'm going to integrate from 1 to 8 and divide by 8 minus 1. So 1/7 of the integral from 1 to 8 of f of x dx. So 1/7 of 30. That's why we did that, so we can find this value. And say it's 30 divided by 7, or whatever. Okay, find the average value of f on the indicated interval. Oh, yeah, let's just do some geometry. We don't want to do that. We can't do that. We don't know how to anti-differentiate this thing. It is possible using a trig substitution, but that's not really part of AP Calculus, and not something we're ever going to do in this class. We're going to use geometry instead. We're going to kind of use our own cleverness to figure out these integrals rather than doing long, painful trig substitutions and things like that. We don't want that. All right. So this one, on -4 to 2, okay, that's the whole thing. Okay, write the integral, and that's going to be 1/6 of the total area, and this is a triangle with a base of 6 and a height of 3. So that's got area half of 18, which is 9. So I've got 9 divided by 6. Okay, which is 1.5, which does seem kind of reasonable for an average there. I mean, we don't know really what it looks like, but it seems possible. Okay, now this, we need to figure out the area underneath the semicircle. And I don't know that we need to do that this year, except for maybe on the first day of school when I gave you like a geometry quiz or something. All right, so I'm going to say on the interval -1 to 1, it'll be 1 over 1 minus -1, integral from -1 to 1. Okay, this appears to be a circle with radius 1. Okay, so the half circle that I'm going to shade in red, that has area 1/2 of pi times radius squared would be 1 squared, so it's just pi over 2. Now the whole thing is 2 units, right? Because there's 1 unit right there and 1 unit right here. So the area of the white region is going to be 2 minus the area of the red region. So that. And if I just had to simplify that, then I would say that would be 1 minus pi over 4. And that's all I got for you for this video.